Hello students, in today's video we are going to cover Ahwa principle, Pauli's exclusion principle, Hund's rule of maximum multiplicity and some of the applications in atomic structure. Okay, let's start our video today with Ahwa principle. What is meant by Ahwa principle? See, in the previous session we have done with the quantum numbers. In that quantum numbers, how the electrons will accommodate in each of the orbital we have learned, right? So n helps to accommodate orbit number and L gives the orbital number and M gives in which orientation, means in which degenerate orbital electron will present, and S will give the information about either we are talking about the first electron or second electron, isn't it? So if we know the quantum numbers perfectly, then we are able to write its electronic configuration and we are able to identify where the electron exactly present in an atom, right? So what is the Ahwa principle? So in an atom, electrons are entering, right? S orbital can accommodate 2 electrons, p orbital can accommodate 6 electrons, d orbital can accommodate 10 electrons, f orbital can accommodate 14 electrons, right? So these electrons, how they will enter and how the electron enter into which orbital first, that is what explained by Ahwa principle. So generally energy depends upon the n, means n increases, energy of the orbital increases, n value decreases, the energy of the orbital also decreases. So what is Ahwa principle? The electrons will enter into the orbital which has the lowest energy first. Electrons enter first into the lowest energy orbital. That lowest energy orbital, how to find? That is what helps the Euler diagram we have. 1s, 2s, 3s, 4s, 5s, then 2p, 3p, 4p, 5p. While talking about the 4d, 5d and 6d, like that we will write. And here you can get one doubt. Why we are writing 1s, 2s, 3, right? And like that only we can start p orbital also with 1, right? 1p does not exist, and d also starts from 3d, d orbital starts from 3d. 2d does not exist, 1p, 2d does not exist. Why these are not existing? See the clarity here. For 1p orbital, what is the n value? N value is 1. What is the L value for p orbital? As we discussed in the previous, L value is 0, that is s orbital. L value equal to 1 p orbital. L value is 2 d orbital. L value is 3 f orbital. Here 1p is there. So what is the L value for p orbital here? 1. If you observe, n value 1, L value also 1, but n is independent, but L depends on n. Always L value should be less than n, but if you observe in 1p, n and L are equal. So this is not existing because of that reason. Whereas come to 2d, why d orbital is starting from 3 orbit? Why d orbital is not starting from 1 or first orbit or second orbit? Why 1d is not existing? Why 2d is not existing? Why d orbital starts from 3? The reason, write for 2d, n value is 2. What about the L? L value for d orbital is 2. Is it possible? N equal to L? No. N is greater than L always. So 2d is also not possible. If you take the 3d, n value is 3, but L value is 2 for d. So d. So this is according to the condition. N is 3, L is 2. That's why d orbital starts from the third orbit or third shell. Okay. So here I want to give one more clarity also here. If you see, suppose it is an atom. First it is a nucleus. It is the first orbit, it is the second orbit, and it is the third orbit. Like first orbital has only 2 electrons because only 1s is possible. Whereas come to the second, here s and p orbitals only will be there in the second because d orbital will not enter. That's why 2d is not possible. Just now we discussed. Whereas come to the s, p, d starts from the 3. If you see, s orbital can accommodate 2 electrons, Whereas come to the P, S can accommodate 2, P can accommodate 6. 6 plus 2 in the second orbit 8 electrons will be present. SPD, S can have 2 electrons, P orbital 6 electrons, D orbitals 10 electrons. 10 plus 6 plus 2, total how many? 18 electrons. That is the way of arranging the electrons. First orbit 1s, second orbit 2s, 2p is also possible. Third orbit 3s, 3p, 3d. That is the order of accommodating the electrons. And even this count, first orbit has 2 electrons, second orbit has 6 electrons, third orbit has 8 electrons. This is already in Bohr's atomic model with 2n square formula Bohr has approved, isn't it? So this is the perfect theory of the electrons accommodating in the each orbit, and the count is also similar and it is unique, right? So what is Hofbauer principle is explaining, while the electrons are accommodating, lowest orbital will take the electrons first. Electrons enter into the lowest orbital first. So here you can get one doubt. Suppose 1s is there, 2s is there. Second orbit if you come 2s, 2p, 2d. 2s is there, 2p is there, not 2d. Here lowest means according to the n value you are telling 1s, 2s if you observe n equal to 1, n equal to 2, so n equal to 1 that has the lowest orbital. And here comes to the 2s and 2p. N value is same for both, then how come we know which has the lowest energy? Because n value is both same for 2s and 2p. Then we have to follow n plus L rule. N plus L rule means n value is 2 here. What is the L value? For s orbital L is 0. 2p, n equal to 2, but L value for p orbital is 1. 2 plus 0 is 2. 2 plus 1 is 3. N plus L value for 2s is 2. N plus L value for 2p is 3. Which has the lowest value? 2s. So electrons enter into 2s orbital first after 1s. Next electrons enter into 2p. So what is the Hofbauer? Electrons enter into the lowest energy level first. How to identify which has the lowest energy? That depends upon the n value. If n value is lesser, then electrons enter into that first. If in case any two orbitals has the same n value, what we have to do? We have to follow n plus L rule. What is n plus L rule? N and L value we have to find out and then add which orbital has the n plus L value lower, then electrons enter into that orbital first. This is the Hofbauer principle, right? Now comes to the next one. Next one is the Pauli's exclusion principle. What is Pauli's exclusion principle? As we discussed about the quantum numbers, how many quantum numbers we have? We have 4 quantum numbers. Principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. Means n, L, m and s. N, L, m, s. Right? So n principal, L. So what is the Pauli's exclusion principle? No two electrons in an atom will have same set of 4 quantum numbers. At least they differ in their spin quantum number. I will explain this statement with one example. I am taking the helium atom. I am taking helium. What is that helium? Helium atomic number is 1s2. Means in this it has 2 electrons. Isn't it? 2 electrons. S has no orientation, so it has only 1 orbital. So it is the 1s1 first electron, 1s2 second electron. Here we are not supposed to represent the electrons in this way. See, both should be in the opposite spin. First electron positive, second electron is negative. This type of filling of electrons is not correct, because S spin quantum number plus half for first electron, second half for minus electron. One is in clockwise direction, the another one is in anti-clockwise direction. If you write the representation of electrons like this, both are in clockwise means or both are in anti-clockwise like, so We will not follow this. This is the one electron will rotate in clockwise, another electron will rotate in anti-clockwise direction. So that's why the representation of electrons in an orbit will be like this. Okay. Now come to the point. Now I want to write 4 quantum numbers for the first electron, right? So N, L, M and S. What is the N value here? 1. L value for 1s orbital, L equal to 0 for s orbital. So L will be 0. Obviously L is 0, M also will be 0 because M value between minus L to plus L including 0. Here L value is 0, obviously M also 0. What about the spin quantum number? While we are talking about the first electron in an atom, it takes plus half, clockwise direction. So plus half, I am giving here plus half. Whereas now I want to write for this second electron the 4 quantum numbers. For second electron, all the principal quantum number N will be same 1. L is for s orbital, L value is 0. M also 0. Whereas come to the S, we are talking about the second electron which is in anti-clockwise direction. So it gives minus half. The spin is minus half. So if we observe here, helium is an atom. That atom has 2 electrons. That 2 electrons for we have written 4 quantum numbers. The first 3 quantum numbers are same, but that is differed in spin quantum number. That is the statement, no 2 electrons in an atom will have same set of 4 quantum numbers. At least they differ in their spin quantum number value. Got it? So that is called Pauli's exclusion principle. Because of this spin, we cannot get confusion. Even N, L, M can be same, but at spin we can identify either we are talking about the first electron in that orbital or second electron in that orbital, like, right? So this is called Pauli's exclusion principle. Now come to the Hund's rule of maximum multiplicity. What is meant by Hund's rule? While talking about the magnetic quantum number, we have studied about degeneracy. Degeneracy is nothing but the orientation of the electron. In p orbital, there is the 3 orientations, that is px, py, pz. That orbital, that dumbbell shape, on px axis, y axis, z axis, the orientation is different. Magnetic quantum number gives the information about the spatial orientation of the particular electron, isn't it? So here, what is the Hund's rule is explaining here? All the degenerate orbitals, while filling up the electrons into an orbital, the degenerate orbital should fill first with 1 electron, then only we should pair up. For this, I will take 2 examples, that is nitrogen and oxygen. I will take carbon, nitrogen and oxygen, right? So here carbon, nitrogen and oxygen. Carbon's atomic number is 6, nitrogen's atomic number is 7, oxygen's atomic number is 8. Electronic configuration for carbon is 1s2, 2s2, 2p2. For 7, 1s2, 2s2, 2p3. For this, 1s2, 2s2, 2p4. This S already those we know, but here our topic is about the P because it has the orientation. What is that P? P has 3 orientation. One is px, py and pz. Px, py and pz, right? Px, py and pz. Here comes to the carbon, P has 2 electrons. What is Hund? That 2 electrons are not supposed to fill in this way. Each degenerate orbital should fill with 1 electron first, means px, py. So px 1 electron, py 1 electron. Comes to the nitrogen, 2p3 means P has 3 electrons in that. So that 3 electrons, how they should accommodate? Px 1 electron, py 1 electron, pz 1 electron. So we are not supposed to write like this. First 2 electrons px immediately we send, then 1 electron is there, that 1 electron I will send to py, I will keep pz 0. Is not possible. All the degenerate orbitals should fill first. Comes to the oxygen, how many electrons are there in p orbital in the oxygen? 4 electrons. 4 means actually here in the px I will send 2 electrons, py I will send 2 electrons, I will keep pz 0. Wrong. What is the process? P has 4, so first 1 electron in px, second electron in py, third electron in pz, that fourth electron now again comes to the px. All the degenerate orbitals should fill with 1 electron first, then they should pair up. That is called Hund's rule, right? I think you got this Hund's rule of maximum multiplicity. If you are not accommodating the electrons in that way, that is the violation of the Hund's rule. We have to follow Aufbau principle, we have to follow Hund's rule. Based on those only we have to write the electronic configuration. What is the electronic configuration? The arrangement of the electrons in a particular order in the given orbitals. In a classroom, I will make to sit the students in a particular order, for each bench 2 or for each bench 3, like that. So that arrangement of the electrons, the arrangement of the students in the classroom, like that only the arrangement of the electrons in an orbit or orbital. This gives you the information about the structure of an atom. That is what we are studying, right? So this is the Hund's rule of maximum multiplicity. So maximum topics we have covered in the atomic structure, but I want to go through some of the applications here. Means what is the data given, in which formula we have to substitute the given data, how to identify that formula is important while doing the applications in either physical chemistry or in general chemistry, right? So let us see here. Calculate the energy associated with photon of light whose frequency is 3 into 10 to the power of 15 hertz. Means here the given frequency they are asking to calculate the energy. So after reading the problem, first we should immediately think that what is the relation between energy and frequency. It is in Planck's quantum theory, E proportional to nu, E equal to h nu, E equal to h nu, E proportional to nu, E equal to h nu. It is the Planck's quantum theory. Already we discussed that Planck's quantum theory, right? So h is the Planck's quantum theory, nu is the frequency. We have to find the energy. So E equal to h value already we know 6.625 into 10 to the power of minus 31 joules, right? 34 joules, sorry. H is equal to 6.625 into 10 to the power of minus 34 joules, or if you want to take in the ergs 10 to the power of minus 27 also we can take, and into what is the frequency they have given, it is joule second. What is the H? Joule second is the unit. 3 into 10 to the power of 15. Hertz is nothing but second inverse. So here these hertz and these seconds we can get cancelled. If you multiply this with 6.625 into 3, we will get the answer. Then we have to choose the correct answer in here. Do this multiplication and find out the correct option. Why I have taken H value in joule? In the given options, H value, in the given options answer is in joules. That's why I have taken the H value in joules. In the options, if they have given ergs, then H value you have to take in the ergs. This is the way of the problem to do, right? Now comes to the next problem. Calculate the uncertainty in velocity. When we study that uncertainty in velocity, immediately in our brain it should strike that, okay, this problem is regarding to Heisenberg's uncertainty principle. So what is the formula for Heisenberg's uncertainty principle? Delta x into m into delta v is greater than or equal to h by 4 pi. Then delta x into m into delta v is nothing but change in momentum, delta p. Okay. So delta v is greater than or equal to h by 4 pi into m. So now read, this is the formula. Now read the question. Calculate the uncertainty in the velocity of a cricket ball of mass 150 grams. Mass is given, how much? 150 grams. If the uncertainty in its position is of the order of 1 angstroms, uncertainty in its position is nothing but delta x value is given, that is 1 angstrom. And So he is asking to calculate the delta V. What is the delta V value? Delta X is there, H is 6.625 Planck's constant value, we have to substitute. 4 into pi value 3.14 constant we can substitute, and M is given in 150 grams. But once see here, H value they given 6.6 into 10 to the power of minus 34 kg meter seconds. In MKS system they have given. So throughout the problem we have to maintain the same units, means this angstroms you have to convert into meters, and this 150 grams you have to convert into kg. So 150 grams will convert into 150 in 10 to the power of minus 3, and 1 angstrom in meters is 10 to the power of minus 10 meters, isn't it? So then we have to substitute, and then we have to find the problem. So this is the way of using the given data and the formula. Then all you can substitute and we can write. I want delta V. Then H by 4 pi m into delta x. We have all the values. H value 6.625 into 10 to the power of minus 34 they given, by 4 into pi value 3.14 into m value 150 into 10 to the power of minus 3 into delta x value 10 to the power of minus 10 meters. So do this calculation and find out the value, right? So this is the way of doing the application part, right? Comes to the next one. Which of the following configurations violates Hund's rule? Just now we discussed the Hund's rule. What is the Hund's rule? All the degenerate orbitals should fill first, then only they should pair up. So just check the first option. 1s, only one orbital is there, so it is s orbital, it is p orbital, s, p. All s has only one orientation, so what is given for s orbital is correct. Comes to the p. The electrons d, px, py, pz, px, py, pz, px, py, pz. So all the degenerate orbitals in A, B, C options fill with one electron. Comes to the d. Here pz they kept 0, no electrons in pz, but px has 2 electrons. According to the Hund's rule, it is violating the Hund's rule. Px should fill with 1, py should fill with 1, pz should fill with one electron. So all the 3 electrons should fill with, all the 3 electrons should enter into px, py, pz, then only 4th electron should come into px. That is the order. So according to the given, which of the following configuration violates? D option is violating the Hund's rule. Okay. Now, which of the following sets of quantum number is correct for an electron in 4f orbital? So in 4f orbital, which of the quantum number is correct, he is asking. Let us try to write first our quantum numbers. 4f is given. He did not mention in which degenerate orbital, which electron also he did not mention, just they given information about the 4f. So compulsory n is 4 and L value for f orbital is 3. For s orbital L is 0, for p orbital L is 1, for d orbital L is 2, like that. For L, f is 3. Let us check first option. N equal to 4, L equal to 3. Okay, correct. N value is correct, L value is correct. But come to the M. What we said, M value always should be within the limit of L. That is nothing but M value should be in between minus 3 to plus 3 including 0. But in the first option M is given plus 4. M always equal or less than L, not greater than L. So this quantum number is not possible. Comes to here, n equal to 4, L equal to 4, but given f orbital L should be 3. So second option is also wrong. And also he given n and L have same values, but that is also wrong, because always L value should be less than n. But here he given equal to. So B option is also wrong. Comes to the D here. N is 3 he said, but 4f orbital means what is the n value? 4. L is 2 given, F orbital L value 3. So NL all values only he given wrong. So D option is wrong. Check the C. N equal to 4, correct. L equal to 3, correct. For M, value should be within the limits of L. L is 3, it is plus 1. Obviously, minus 3 to plus 3, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. M should have these values when L equal to 3. So it has plus 1. It is within the order. So M is also correct. Yes, plus half. It can be plus half or minus half because he didn't mention the particular electron in the problem, in the question. That's why it can be plus half or minus half. So our correct answer is C. Right? So like this we have to do the quantum numbers problems. Right? So thank you. Okay guys, we have completed the important topics in atomic structure. In next video we will come with the next topic. So as of now we have finished the atomic structure and some of the application parts also. Okay, do watch our video. Thank you so much.